Hello everyone, welcome back. By now we have discussed about various chemical, physical and rheological properties of bitumen. Today we will start discussing about the grading of bitumen, which is basically done to differentiate between the bitumen samples which we get from different crude sources. Also, this grading system is used to select the bitumen for construction purposes, and this grading system is essentially related to these physical and rheological properties which we have discussed in our previous lectures. Starting with the grading of bitumen, during the initial period when, that is up to 1900s, most of the bitumen were not from the conventional refinery process which we use today. As we have discussed previously, that before 1900s, before the crude refining became common, mostly natural bitumen was used for the construction of pavement, and during that time there were only few sources of this natural deposit. For example, Trinidad Lake bitumen was one of them. So, simple process such as appearance of the bitumen sample and its solubility in carbon disulfide, because if you remember, this natural bitumen had high content of other mineral matters. So, the solubility in carbon disulfide, these were used for checking the bitumen quality. Later, after the manufacturing of bitumen started, there was a necessity to develop alternate methods so that bitumen with different consistency can be differentiated with each other. Different crude sources will produce different types of bitumen, and the selection of bitumen required more, or you can say rational or better process for selection or for grading. During that time, around 1888, H.C. Bowen, he invented the penetration machine or the penetrometer, which we commonly call today. Various modifications were made to this penetration machine, the one which we use today. It has the initial penetrometer had undergone various changes which were done by ASTM and Federal Highway Administration, that was called as Bureau of Public Roads during that time. So, they made several changes before adopting it in the specification. During the similar period, another crude method which was used was the Shearing test. So, this is a very interesting test where an asphalt specialist used to take a sample of bitumen, and by the amount of pressure he required to apply to chew the bitumen between his teeth, he used to predict by this pressure, he used to tell about the consistency of bitumen. In 1918, the first specification by Bureau of Public Roads was developed, which was based on penetration of bitumen at 25 degree Celsius, and this we have discussed why this 25 degree Celsius was specially chosen. This was because this represented the average service temperature of the pavement, especially in US, and this was published by ASHO, which is the American Association of State Highway Officials, in 1931. Various grades of bitumen as per the penetration value were defined. For example, there were grades such as 40-50, 60-70, etc. Just to remind you again, what do you understand by the grade 40-50? By the grade 40-50 we understand that the penetration of the needle under standard condition will range from 4 to 5 mm in the penetrometer when we penetrate the needle in the bitumen sample. So, this is basically a bitumen which will be graded as 40-50. Similarly, 60-70 indicates a bitumen where the penetration of the needle will be somewhere between 6 to 7 mm and so on. So, based on this penetration value, different grades of bitumen or the consistency of the bitumen can be defined. Let us talk about some of the advantages and disadvantages of this penetration grade bitumen. One of the advantages of penetration grade bitumen is that it is simple to use. The equipment is cheaper, it can be handled by a normal manpower. You do not need a specially technical staff to handle this equipment, and it is also portable. It can be taken to different places, to different sites for testing the bitumen sample. If we talk about the disadvantages of penetration test or penetration grading, one disadvantage is that this is an empirical test. We are not testing any fundamental property of the material here. Another disadvantage is, if you remember, we have discussed about this, that here the bitumen sample is subjected to a very high and non-uniform shear rate, which depends actually on the consistency of bitumen during the test. Also, it is possible because we are testing the bitumen at one particular temperature and the penetration value at that particular temperature is used to grade the bitumen or define the consistency of bitumen. So, this example shows that we can have bitumen samples, 3 different bitumen samples having the same penetration at 25 degrees Celsius, but they can behave very much differently from each other if you compare a range of temperature, which means that the temperature susceptibility of the bitumen can be very different from each other, alright. But if we talk only about the consistency at 25 degrees Celsius, then all the bitumen will be graded as the same binder, which may not be rational. So, then further around 1960s, researchers and agencies, they thought that they needed some more fundamental property to grade the bitumen samples, and therefore they selected the viscosity of the bitumen at 60 degrees Celsius as the basis for grading or defining the consistency of bitumen. And there were several reasons why the viscosity was chosen. One is that viscosity is a fundamental property of the material, so it does not depend on the testing system. So, this is a property of the or the fundamental property of the material. Also, the choice of 60 degrees Celsius will ensure that we are testing the performance of the binder with respect to its rutting resistance. Similar to this, when penetration grade came, the 25 degrees Celsius was also chosen so that the results can be compared with the occurrence of fatigue cracking or low temperature cracking. Likewise, in the viscosity grading system, the temperature 60 degrees Celsius is important because at this temperature the permanent deformation characteristics of the binder can be related. As I said, this is a fundamental test in comparison to the penetration test, and also the reason of choosing 60 degrees Celsius during that development was because this was the average maximum surface temperature in the US during hot summers. Parallelly, during 1960s again, the California Department of Highways, they were developing similar specification which required measuring the viscosity of the binder, but they did this on the short term residue or the aged residue, okay. And this was done because they found that some of the binders, when in the unaged condition, they have the same consistency. After aging, after undergoing mixing with the aggregates, few of these binders becomes or yields tender mixes. So, they do not compact properly under the rollers. In order to differentiate these bitumens or to solve the problem of tender mixes, they found it more logical that bitumen should be graded after undergoing the short term aging, because only after short term aging this is used in the field, and this will also ensure that asphalt binders after mixing, they will behave similarly during the construction process. In the viscosity grading, several viscosity grades were defined by the ASTM standard and the AASHTO standard. So, this is AC 2.5, AC 5, and we have grades up to AC 40. So, this 2.5, AC 2.5 or AC 5, what does it mean? AC 2.5 indicates that the viscosity in poises at 60 degrees Celsius will be 2.5 into 10 is to power 3, which is 250 poises at 60 degrees Celsius, alright. Similarly, for example, AC 40 means that the viscosity will be 4000 plus minus something of, or if this is a minimum or a one side specification, it can be minimum 4000 poises at 60 degrees Celsius. In addition, in this grading system, in addition to the viscosity of the binder, there are several other tests which are conducted or which were conducted such as penetration at 25 degrees Celsius. So, this can control the consistency at the intermediate temperature range. 60 degrees Celsius can control the consistency at the average maximum temperature range, whereas viscosity at 135 degrees Celsius will control the consistency at higher temperatures. So, since 3 temperatures are used to control the consistency, we have more control over the temperature susceptibility of different bitumen samples. Additionally, safety test, which is the we have also learned about the Cleveland open cup apparatus where flash and fire point test is done. So, this test was also included, and they also had a provision of doing the ductility test on short term aged binder at 25 degrees Celsius. So, this were the requirements of the viscosity grading system. So, this figure it shows that how different temperature ranges are controlled here. Different temperature ranges talking about the average service temperature, mixing compaction temperature and hot summers temperatures. Talking about the advantages and disadvantages of the viscosity test, if we talk about the advantages, viscosity test measures one of the fundamental properties. It can control the rutting resistance during hot summers. Since consistency is measured at 3 temperatures, we have more control over the temperature susceptibility. And if we talk about the disadvantages, one disadvantage is, which may not be truly a disadvantage, but yes, in comparison to the penetration test, the viscosity apparatus is more costly. And using the viscosity value, we are not able to predict or understand about the intermediate and low temperature properties of the bitumen sample. Since we have talked about the development or of the penetration grade and the viscosity grade, let us see that how and when in India we adopted different specification. So, the first specification for grading of bitumen, it came in 1950, which was titled as specification for asphaltic bitumen and fluxed mastic asphalt for road making purposes. Later on, they removed the criteria for fluxed mastic so that only paving grade can be considered. So, this first revision included only the paving grade bitumen, and it also accommodated parallelly the test methods on the bitumens, different tests which are required to be done on bitumen, and this test can be done using the specification IS 12012 1220, which was developed in 1958. Alright. So, this is methods for testing tar and bitumen. In the second revision, which came in 1992, few changes were made because IS 1201 to 1220, which was initially developed in 1958, also underwent some revision in 1978. So, in order to incorporate those revised standards, the standard of grading the bitumen was also revised. And during those times, because the process in the refinery were not highly controlled as we have today, so there were waxy and non-waxy crude bitumens. So, it was found that bitumen with high wax content at low temperatures, they are more susceptible to thermal cracking because they become very stiff, and at high temperatures they become excessively soft. Though these different bitumens, the non-waxy and waxy bitumens, can have the same consistency at intermediate temperature, but at very low temperature and very high temperature they showed very different behaviors. So, that is why two different tables were produced, which I will be showing you in the next slide, to grade the bitumen under the waxy and non-waxy crude grades. And this specification up to 1992 was based on the penetration value. So, we adopted the penetration grade, which was similar to the penetration grade developed in US. The third revision came very late, around 2006. Here we started using the viscosity grading system, and in India we define the viscosity grading system or the viscosity grade as VGX, where VG denotes the viscosity grade and X is a number, again which represents the viscosity of the binder at 60 degrees Celsius, similar to the AC grades which we have talked about in the previous slide. So, here for example, if you talk about VG30, so this is a binder whose viscosity is 30 into 100 plus minus X poises, at 60 degrees Celsius. This value of x, it will change from grade to grade, which I will show you in the subsequent slides. Further, the 2006 specification was refined in 2013 with some additional provisions, which we will see the table and we will try to see that what was the major difference in the specification given in 2006 and 2013. All right. So, well, this is just a snapshot taken from the code IS 73/1992, and you can see that you have two tables here for bitumen type 1 for waxy and non-waxy grades. And here one important point to note is that there are 13 different tests which are required to be done in order to grade the bitumen, all right. And this was a penetration grade where 35 indicated the penetration, average penetration value, you see, therefore the penetration is between 30 to 40, all right. And similarly we have grades up to S200, whereas in type 2 we have grades from A35 to A90. So, you can see that some of the interesting things to note down here is that during that time we used to do penetration ratio, where penetration ratio was defined as the ratio of penetration at 4 degrees Celsius to the ratio of penetration at 25 degrees Celsius. Why I am highlighting this is because today we no longer use the penetration value at 4 degrees Celsius, or we do not conduct the test. Paraffin wax content test, again we do not do it today. Ductility test was done on unaged binder, and today we do it on short term aged binder or thin film oven or RTFO aged binder. Then that time we used to determine water percent by mass, we no longer do this test today. That time we used to carry out the low temperature test. I find this test to be important, but since we are in a tropical climate, we do not no longer use this test in our specification now. Similarly, retained penetration we no longer measure, and we also do not measure the loss on heating. So, there are several tests which were done during that time, and now the number of tests have reduced considerably. So, this is again taken from the further revisions. So, 2006 you can see. So, here we started using the viscosity grading system, and therefore, you see that we have like VG10 to VG40 here. Before that, let us see the requirement of the number of tests. You can see only 7 tests are required in comparison to the previous revision. In 2013, they gave additionally this table where based on the 7-day average maximum air temperature of the location where we are doing the construction, you can choose the appropriate binder. For example, if 7-day average maximum air temperature is more than 45 degrees Celsius, then you have to use VG40. If it is between 38 to 45, VG30 and so on, all right. So, so this is something which was new. And again, if you see, we have only 7 tests to be done as per the 2013 revision, but let us compare the 2006 and 2013 because they both are the viscosity grading system. In 2006, if you see, the requirement of absolute viscosity is based on the minimum criteria, all right. So, VG10 means that the viscosity minimum should be 800 poises at 60 degrees Celsius, whereas here the requirement of absolute viscosity is provided in a range. So, this is if it is VG10. So, as I said 10 into 100 plus minus 200 poises. If it is VG40, 40 into 100 plus minus 800 poises, all right. So, in this way the viscosity is given in a range rather than a minimum value. Similarly, the penetration value at 25 degrees Celsius is given in a range in the 2006 version, whereas here if you see that the penetration is given as a minimum criteria. Well, these are the two prominent changes which were done in the 2013 revision in comparison to the 2006 revision. Having discussed about the penetration grade and viscosity grading of bitumen, let us now talk about the super pave grading system. and which uses the rheological parameters in contrast to the physical properties such as penetration and viscosity to classify or grade different bitumen samples. The Super Piff criteria was developed through the Strategic Highway Research Program, which was a 5-year research program and launched in 1987. This was actually a $150 million project, but out of the entire amount $50 million were used or were invested to develop the performance based specification for asphalt binders and mixtures, which resulted in the development of Super Pave mix design criteria, where Super Pave stands for superior performing asphalt pavements, and it also resulted in the development of the performance graded asphalt binder grading system, which we also call as the PG grading system. Okay, and this was developed somewhere around mid 1990s. Now, the important question is that why was there a need to develop the Super Pave grading system? What were the issues in the viscosity graded system due to which the researchers started working towards another grading system, which is the Super Pave grading system? One of the main reasons were that the existing specifications were mostly empirical in nature. Most of the consistency tests which were required to be done on bitumen to classify them, to assess the consistency or the behavior were empirical in nature. Another problem was, irrespective of the location where we are going to use this binder. Let us say if you talk about India, we can have a variety of temperature conditions. In the extreme northern side, we can have, during the summers we can have very high temperatures, and the pavement temperature can be as high as 70 degrees Celsius. On the other hand, in locations, extreme locations such as northeastern regions or Himalayan regions, we have extremely low temperatures. Since bitumen is a viscoelastic material, by now we understand that the response of the bitumen to the loading condition will definitely be a function of temperature and loading conditions or the frequency of load. So, therefore, doing or carrying out tests on bitumen for its classification based on a single temperature or only one temperature seems to be irrational, and this was also one of the reason which was highlighted, which prompted the researchers to work on a better grading system. Earlier, we used to carry out the test at the same test temperatures irrespective of the project locations. If we see the specifications of the viscosity grading system and penetration grading system, you will see that there was a requirement to do the ductility test after short term aging of the binder, which or viscosity ratio after short term aging of the binder, which means that only short term aging of the binder was done to assess the durability characteristics. However, we have discussed in detail that durability is also a function of the long term behavior of the binder when the binder is exposed to the average temperature conditions during its entire service life, which is just after opening to the traffic to the end of its service life. It undergoes a lot of temperature changes. However, long term aging was not considered in the previous specifications. It was also observed that in the viscosity grading system, which was the earlier specification, binders can have different temperature susceptibility and different performance characteristics, even though they fall under the same grading system with respect to the viscosity grading system. This I will show you in the next slide through a graph. Another point which was noted was that the previous specifications were mostly applicable for unmodified binder. For example, if you talk about the experimentation, we have discussed that if polymer modified binders or crumb rubber modified binders, they are used in a capillary tube, it can choke the tube, it can give you unrealistic results. So, these issues were identified which required, which necessitated to develop better grading system, and which resulted basically in the Super Pave grading system. This graph shows that you can have 3 binders And let us see what are the specifications here. Let us say we have the specification for a range of viscosity at 60 degrees Celsius. So, you see you have bitumen A, B and C, they all have the same range of stiffness at 60 degrees Celsius, and let us say this is the upper limit and this is the lower limit as per the specification. The viscosity grading system requires a minimum penetration value at 25 degrees Celsius. So, if this is 25 degrees Celsius, then all these 3 bitumens has the minimum penetration value at 25 degrees Celsius. Similarly, at high temperature or 135 degrees Celsius, there is a requirement that there should be a minimum viscosity, or you can say maximum viscosity of the bitumen sample for pumping criteria. So, here all the 3 bitumens satisfy that criteria. If we are given these 3 bitumen A, B and C and we are asked to grade this bitumen, we will actually end up grading this bitumen under the same grade. However, you can see that the variation of stiffness with respect to temperature is very much different for all the 3 binders, which means when these binders are exposed to actual field conditions at different locations, and these locations can have very different rate of change of temperature with time. So, this bitumen will behave completely differently, alright. So, this is again one of the reason which required the development of a better specification system for bitumen. So, one of the unique feature of super pave grading system which we will be discussing is that the specified criteria it remains constant, but the temperature at which the criteria must be achieved it changes for various grades. Now, let us again try to understand this statement. It might appear to be confusing at the first time. So, we will try to understand in reference to what we do in the usual specification. So, in the usual specification, as we have discussed, if it is a viscosity grading system, we will carry out the viscosity grade at 60 degrees Celsius and we will report the value. So, this value is variable, depends on the consistency of bitumen, but the temperature at which I am carrying out the test is constant 60 degrees Celsius irrespective of wherever I am going to use this bitumen. Now, in the super pave grading system, what they have done that the specified criteria remains constant. So, here with reference to viscosity, I will say that the value of viscosity will be constant, but the temperature at which this value of viscosity is reached by different bitumens, or the temperature at which this criteria must be achieved will vary from grade to grade, from project to project. So, let us say we have identified that if a bitumen has a viscosity of 4000 poises, let us say. So, if a bitumen has a minimum viscosity of 4000 poises, this can give you a satisfactory performance with respect to rutting at locations where the temperature is 60 degrees Celsius, let us say. This means that I am fixing this 4000 poises. Now, I will select the bitumen for this location where the average pavement temperature, maximum pavement temperature is 60 degrees Celsius, ensuring that the viscosity of the bitumen which I am going to use is minimum 4000 poises, alright. So, this is what is different in the super pave specification, that the parameter will, the value of the parameter will remain constant, but the temperature at which this parameter should be met or will be met by a binder will change from grade to grade. In super pave, we are measuring parameters or properties of the binder which can directly be related to the field performance, alright, and through engineering principles, which means we are here testing more fundamental properties of the binder, and these are not empirical in nature. We test the binders at a range of temperature, which means that we are not restricting our test for one temperature for a particular test. A single test can be run at different temperatures, and these test temperatures are chosen such that, or these temperatures will tell us about the range of temperature which the bitumen will encounter in the actual practice or in service. Specifications for selecting the binder on the basis of critical distress. So, here the target is to select a binder so that this binder is able to resist the critical distresses, and this critical distresses are permanent deformation or rutting which occurs at higher temperature or higher average maximum temperature of the pavement in service, fatigue cracking which takes place usually at intermediate temperature ranges, and low temperature cracking which is a non-load associated cracking, or you can say thermal cracking. Okay. So, since these are the three critical distresses, we are going to test the binder to see if the binder can resist these three failure criteria at the location where we are going to use it. Here in this presentation we are not going to discuss again about the test process. All the tests we have already covered in our previous presentation, but let us see that in super pave grading criteria what are the tests which are required to be done. So, here we will use RTFO and PAV. By now we understand what an RTFO is and what PAV is. So, they are used to simulate the aging of the binder, and since they are used to simulate the aging of the binder, they basically measure or are used to assess the resistance of the binder to aging or to assess the durability characteristics of the binder during construction and also in service life. So, if we are interested during construction, we will be looking at the short term aged samples. If we are interested in service condition, we will be looking at the PAV aged samples. Then we use dynamic shear rheometer. Dynamic shear rheometer will measure the properties at high and intermediate temperature, not at extremely low temperature, which means DSR is essentially used to assess the rutting and fatigue characteristics of the bitumen. Then we have rotational viscometer, which is usually done on samples in unaged condition, and here we are assessing the properties of the binder at higher temperatures, which is used to assess the handling and pumping characteristics of the bitumen in the mixing plant. Then we have bending beam rheometer. This is maybe a new term for us now. I am sorry for this, this should be direct tension tester. So, this is direct tension tester, and they are used to assess the performance at lower temperature and to evaluate the resistance of the bitumen to thermal cracking. Okay. This is a typical grade. Of course, we will be discussing about how this grading system is actually done. So, the grade is written as PG, one number, another number. Okay. So, PG indicates a performance grade. This first term, it represents the 7-day average maximum temperature of the location or of the pavement where we are going to do the construction using this bitumen, and minus 12 it represents the lowest temperature of the location where we are going to do the construction, or which place or which project we are going to select the bitumen sample. And this slide, it shows you the range of temperatures which is covered during the DSR testing. This is just a revision. At higher temperature we are doing rotational viscometer test to assess the pumping and handling characteristics, and this is done on the original binder or the unaged bitumen. Alright. Then after doing the RTFOT, after doing the short term aging and also on the unaged condition, we will do DSR, and this is typically done at the 7-day average maximum temperature of the pavement. Okay. So, for example, this is 64 degrees Celsius here. So, since the project requirement is 64 degrees Celsius, we are doing the testing at 64 degrees Celsius, and we will ensure that the bitumen samples which are tested in unaged condition at 64 degrees Celsius and RTFOT aged condition at 64 degrees Celsius are able to satisfy some standard criteria. We will again do the DSR test at 25 degrees Celsius, but here we will be using the long term aged specimen because we are trying to assess the fatigue cracking related characteristics, and fatigue cracking is a phenomena which occurs when the binder has become stiff and also at the intermediate temperature range. So, binder will become stiff only after long term aging. So, we are using the Pave age samples here, and if you remember from our discussion on rheology that in DSR we have different spindle geometries depending on the stiffness of the binder. If the stiffness of the binder is high, we use 8 mm dia and 2 mm gap. If the stiffness of the bitumen is less, we use 25 mm spindle with 1 mm gap. So, therefore, the geometry is different, but the test is DSR. And at lower temperature, we are going to assess the low temperature characteristics using direct tension tester and bending beam rheometer. And just to tell you that here also we will use Pave aged specimen, because low temperature cracking also depends on the stiffness of the bitumen. So, the binder will be more susceptible when the bitumen is highly stiff, and therefore, we are taking the Pave specimens to do the testing here. All right. Now, let us talk about some of the parameters which are used during the super Pave grading system. So, let us take them one by one. So, for example, let us look at how the testing on or how the rutting parameter is controlled. So, here for the rutting parameter, the test is carried out as we have discussed in the previous slide in unaged and short term aged condition. At which temperature you will do the test? You will do the test at 7-day average maximum temperature of the location for which you are selecting the bitumen. Here we are going to use dynamic shear rheometer, which will be operated in constant stress mode, and we have to ensure that the binder is or we are applying a stress or strain within the linear viscoelastic regime. So, here as per the specification, the strain should be in the range of 10 to 12%, and we do the test at a fixed frequency of 10 radians per second or 1.59 hertz. All right. Then the specification or the criteria is that the value of G star by sin delta, if you again remember, we have discussed that G star by sin delta represents the rutting resistance of the viscoelastic material when it is tested in the DSR. This represents the amount of dissipated energy. So, this should be greater than 1 kPa if the bitumen is in unaged condition, and 2.2 kPa when the bitumen is in short term aged condition or RTFO aged condition. All right. So, this is the entire requirement for rutting characteristics. Now, talking about the fatigue characteristics, this is carried out on long term aged binder, which means Pave aged samples. What is the test temperature? This is the average pavement temperature, which is calculated as average 7-day maximum pavement temperature plus minimum pavement temperature divided by 2 plus 4 degrees Celsius. All right. And for example, if it is, let us say in the previous slide it was 64 minus 12. So, if 64 minus 12 is the grade we are targeting for, then the fatigue will be analyzed or will be fatigue characteristics will be measured at a temperature of 64 plus minus 12 divided by 2 plus 4. So, this is 52 divided by 2 plus 4. So, this is 26 plus 4, this is 30 degree Celsius. All right. So, this will be chosen as the test temperature. Since again this is the PG grading system, the DSR is operated in a constant stress mode, and here at low temperature for intermediate or the fatigue characteristic, the strain should be kept low, about 1% strain. Here it is 10 to 12% strain, and here also the test is done at 10 radians per second. And the criteria is that G star dot sin delta, which we discussed in the previous presentation, is a representation of fatigue characteristics of the bitumen, should be less than 5000 kPa, because lower is the value of G star dot sin delta, more will be the resistance to fatigue cracking. So, there is a maximum limit here, whereas for G star by sin delta it is a minimum limit, because higher is the value of G star by sin delta, more will be the resistance to rutting. Now, you must be wondering that what we have discussed now, and there can be many questions which fundamentally we have to answer before we accept that yes, this is the right way to do it. These questions can be that why these temperatures are chosen, why these aging conditions are chosen, why these parameters have been considered, how the DSR is stress controlled when we are saying that we are targeting for the we are having some target strain values, why 10 radians per second is used and not any other frequency to do the test, and why the specifications have been laid down as 1 kPa, 2.2 kPa or 5000 kPa. So, let us answer these questions one by one. The first question was that why these temperatures? Let us try to understand it in this way, that rutting is a phenomena which will occur during the extended heat waves, alright, during the extended heat waves in hot summer, and it is not a phenomena which will occur only at a single temperature. So, the binder will become soft gradually. So, therefore, the pavement has to be exposed to this extended heat wave or extended high temperature for some period of time, alright, and therefore, the 7-day average maximum temperature has been chosen and not only one single max, because one single maximum temperature can be too conservative, and the 7-day average maximum temperature while developing in US, they assessed the 7-day average maximum temperature based on the weather data of about 20 years. Alright. So, 20 years weather data was taken to define several average maximum temperature ranges or values at which the specifications have been basically developed. Talking about the low temperature cracking, this is basically carried out only at the lowest temperature, not any average low temperature. Okay. So, why lowest temperature is chosen? Because let us understand how low temperature cracking will occur. When the temperature will reduce, the top layer or the HMA will try to contract, and therefore, a tensile stress will be developed between the HMA layer and the base course. If this stress which is developed between these two layers, it exceeds the tensile strength of the HMA layer, the HMA layer will crack, alright. So, which means that even a single low temperature is sufficient to induce the cracking or the thermal cracking in the mixture. So, of course, there are also chances that cycles of low temperature, if let us say the low temperature is not as low to exceed the tensile strength of the HMA, this will not crack. So, at that time we will see that how many cycles are required of low temperature are required to induce the thermal cracking in the HMA mixture. But if let us say there is a drop in temperature to such a level that only one cycle is sufficient to induce thermal cracking in the pavement, so that temperature also becomes a critical concern, and therefore, low temperature cracking is taken. Talking about the intermediate temperature, I showed you a formula. It is maximum plus minimum divided by 2 plus 4 degrees Celsius. Now, this is something which was which came into specification through experience. So, during the SHRP program, there was a task group which was involved in developing this specification, and that time Dr. Dave Anderson, he found that the average temperatures is not only the average of the maximum and minimum, but is little higher than this average, and that little higher is around 4 degrees Celsius. Therefore, they chose or added this 4 degrees Celsius to the average to calculate the temperature at which the fatigue cracking should be estimated or should be assessed, alright. So, this is the reason why these temperatures are chosen. Also, if you want to understand, or if we want to understand about the aging conditions at which these criteria have been developed. So, you see rutting in the hot mix asphalt will typically occur during the first few months or let us say a year of construction, because as time progresses the mix will become stiffer. As mix becomes stiffer, the resistance to rutting increases. So, therefore, we will, if there is a problem in the HMA mixture and not beneath or not in any other layers of the pavement construction. So, if there is a problem in the bituminous mixture, typically the occurrence of crack or occurrence of rutting will be during the first few months of or after the first few months of construction. Therefore, and during this period the binder is exposed only to short term aging or maybe the binder initially is in the unaged condition. Therefore, the unaged binder and RTFO aged binder are used to see the value of G star by sin delta. Whereas, the fatigue cracking is a phenomena which will occur at intermediate temperature range and on stiff binder. So, binder becomes stiff only after long term aging. So, therefore, assessing G star dot sin delta, we are using the long term aged specimen, and similarly for low temperature cracking also stiffness is one of the critical parameter and therefore, PAV age samples are used. All right. Talking about the parameters y G star by sin delta and y G star dot sin delta, this we have already covered in our previous presentation. So, I am not discussing it here, that how they are related to rutting and fatigue respectively. Talking about the stress controlled testing. So, DSR for PG grading is done under a stress control mode. So, what is done here, in order to achieve the target range of 10 to 12% or 1%, the DSR will do an initial adjustment to the torque. So, it will set the stress levels at which this strain can be achieved, alright, and it will maintain that stress level, and therefore, this is a stress control test. Now, I will just do it here. Now, the question is why 10 radians per second. So, I will give you two form of explanations here. One form says that if you see one point and the stress in this particular point. So, studies have shown that load has practically no effect when it is at a distance of 6 into A from the point, alright. So, if this is at a distance of 6 A and this is our point of concern, so beyond this point, if the load is here, this will have no effect. Only when the load comes here, which is at a distance of 6 A from the point, a deflection ball will start appearing for this particular point. Okay. So, similarly there also, this side also it should be 6 A. So, the total deflection ball becomes equal to 12 A. So, if we say that V is equal to D by T, where D is 12 A, and V, let us say we are trying to see a condition which is 80 kmph, for which is an average speed of the vehicle in a highway, and we are trying to find T, this will be around 0.1 second. If you do the calculation, here you can assume that A is approximately equal to 155 mm, alright. So, you will get that T is equal to 0.1 second, but this tells us that the frequency should be actually 10 hertz. So, the question is that why SHRP took 1.59 hertz and or 10 radians per second instead of 10 hertz and not 1.59 hertz. So, well, I could not find any specific explanation to this in different literatures, but what few literature states that since we are using a sinusoidal loading in the DSR, so under the sinusoidal loading 0.1 second is approximately equal to 10 radians per second or 1.59 hertz. Alright. So, this can be, but I am not sure about the derivation at this point, that how sinusoidal loading will produce a an equivalent frequency of, if the time is 0.1 second, how it will produce a frequency of 10 radians per second, but this is the typical explanation in few of the literatures as cited. Now talking about the specifications, so let us talk about 1 kilopascal specification. So as I told you that for the development of the SHRP specification, a special task group was formed by FHWA, and the specifications limit were decided based on consensus by the expert task group. So it is very interesting to note that even this specification has been derived from the viscosity grading system. They found that in US, if the for moderate climates, when the average pavement temperature is 60 degrees Celsius, typically an AC 10 bitumen is used. So several AC 10 bitumens which gave satisfactory performance in US, when they were tested in the DSR at 10 radians per second to evaluate the G star by sine delta value. So it was found that the value is around 1 kPa or greater than 1 kPa. So therefore 1 kPa was developed as the specification. Now talking about the short term aging condition, it is 2.2 kPa. So for this what they did, they evaluated the aging index of these binders. So aging index was calculated as ratio of viscosity of aged and unaged binder, and they found that the ratio of, or the viscosity ratio for these binders, they typically range from around 2.2 to 2.5. So they finally took an average value of 2.2, and therefore the specification of 2.2 into 1 kPa came in, which is 2.2 kPa, alright. So this was the reasons for selecting 1 kPa and 2.2 kPa for G star by sine delta. Talking about the fatigue cracking, again for these binders which were found to be satisfactory, initially they proposed a value of 3000 kPa as the standard initially. So they say that the value should be less, G star dot sine delta should be less than 3000 kPa. So when they gave this specification, many of the binders which were further tested, they failed to meet this conservative specification. Later on they saw that what should be the value at which at least 85% of the sample should pass. So they found that G star dot sine delta, if the limit is set to 5000 kPa, should be satisfactory. So 5000 kPa was thus put as the specification. Moving further, so this was about the high temperature and intermediate temperature performance criteria as per super Pave grading system. Now let us talk about the low temperature criteria. So before I show you any table with these specifications, let us try to understand the test methods. So we have two different tests here which are required to be done. One is bending beam rheometer and the other is direct tension tester. So in the bending beam rheometer, what we are trying to do, we are trying to test the affinity of the bitumen sample to low temperature cracking. What we do in the bending beam rheometer test? We apply a transient creep load on a bitumen beam specimen. So there is a beam specimen of the bitumen which is prepared, and this beam specimen, it is immersed in a fluid. Now since we are trying to do the test at a very low temperature, definitely water bath cannot be used. So we use a mixture of chemicals such as glycol, methanol and water. So we make this mixture or we make this fluid ready. We set the temperature at which we are interested to do the test, and we will just put this beam specimen inside the bath where the test has to be done, and it is maintained at that particular low temperature. Now the dimension of this beam which is taken, because this is a very small beam which is taken, this is chosen to ensure that the Bernoulli-Euler theory of bending prismatic beams can be applied while doing the calculations. So as per this theory, it states that if the section is plane before deformation, it will remain plane after deformation and perpendicular after deformation. So based to satisfy this criteria, the dimension of the beam specimen is chosen. Then we will use a blunt nose shaft to load this specimen. So this is like a 3-point bending test. We are holding the specimen like this, and at the center we are applying the load using a blunt nose shaft. And once we are applying a load, of course you can imagine that this if this is a beam, it will start deflect, it will deflect. If we keep on, if it is a transient load, which means it is increasing with time, so definitely the deflection will also keep on increasing with time. So so load versus deflection data is continuously monitored in the test, and using this data we determine two parameters. One is the creep stiffness. So if you remember from the simple concept of mechanics of solids, that if this is a 3-point bending test, if this is the load P, then delta can be written as PL cube by 48 EI. I mean, this is the conventional formula. So here delta is PL cube by 48, E is the stiffness or the elastic modulus, you can say. I will be 1 by 12 BH cube because this is a rectangular specimen, alright. So here this becomes 4. So if I am interested to find E, this becomes as PL cube by 4 delta BH cube, alright. So this formula is used to calculate the creep stiffness of the beam specimen, and also since we are getting the, or we are monitoring the variation of deflection with time, we try to see that how the slope or the rate of change of stiffness with time is monitored based on the deflection data, and we define a slope at a particular point which is considered as the M value. So let us see that at what point we are finding it out. So here we are using a 100-gram load. Again here why 100-gram load was selected, to ensure that the response of the sample remains in the linear viscoelastic regime. So therefore a 100-gram of load was chosen, and this load is applied for 240 seconds, or you can say 4 minutes. And the creep stiffness is calculated at 60 seconds. Now when initially they wanted to correlate the thermal cracking with the stiffness value, so what literature says that you have to carry out the test for a very long period of time, and the value at which you are targeting is after 2 hours, alright, after 2 hours. But you can understand that 2 hours can be a very long duration for the test to be done. So in order to reduce the timing of the test, what they did, they used the time temperature superposition principle, and if the target temperature is minus 22 degrees Celsius, you will do actually the test at 10 degrees Celsius higher than this temperature. So you will actually do the test at minus 12 degrees Celsius. So how time temperature superposition is used? So you see, you are interested at minus 22 degrees Celsius and you are interested at the value after 2 hours. So if you want to get the response at lower loading time, then of course you have to increase the temperature, which means the response of a viscoelastic material at low temperature and higher loading time is equal to the stiffness of the viscoelastic material at higher temperature and lower loading time. So I hope you can understand or correlate this with the concepts of time temperature superposition principle, which we have learned in the previous classes. So this was used, so therefore this test is done usually at 10 degrees Celsius higher temperature than the anticipated lowest temperature, alright, and this formula, as we discussed, is used to calculate the creep stiffness. So these are some pictures of the test experimental process. So you see, you have a beam specimen of a specified dimension 6.25 into 125 into 12.5 mm. We have a control and data acquisition system. This is the bath which is maintained at that particular temperature at which we are doing the test. This is the beam specimen, this is the notch using which we are applying the load, and then we are monitoring the deflection versus time data, and we are basically taking the deflection value at 60 seconds and using it in the formula which we have discussed to calculate the stiffness. And since we are also monitoring, we can at using deflection at different points, we can find out the stiffness and we can plot the creep stiffness versus time, and at 60 degrees Celsius we see what is the slope here. So try to understand it in this way, that if I want my bitumen to be resistant to thermal cracking, what should I aim for? I should aim for a lower value of creep stiffness, because higher is the stiffness, more will be the affinity to cracking. Here during the test, what is happening, that the bitumen sample is being loaded and it is deforming, is not it. So, there is an energy dissipation which is occurring and there is a relaxation which is occurring. So, the faster my sample will relax, the higher will be its resistance to the loss of energy. So, therefore, I want the M value to be as high as possible, because higher is the M value, it will indicate that the change in stiffness is higher, which means it is able to relax at a much faster rate. Alright. Okay, so, we will see the specification probably in the next slide. Before that, let us discuss about our next test, which is the direct tension test. So, here what was found, that in the BBR test, you see if the stiffness of the bitumen is high, which means it will have more chances to thermal cracking. And of course, the strain tolerance of this binder will be low because it will crack. But for some of the binders, such as polymer modified binders, it may happen that even at low temperatures the binder has very high stiffness, but also has very high strain tolerance, alright, which means there will be much higher resistance to thermal cracking for these bitumens. Therefore, an alternate method, that is direct tension test, was developed to assess these stiff binders which are ductile in nature even at very low temperatures, even when the stiffness of the bitumen is greater than 300 MPa. For these binders, the direct tension test was developed and can be done. So, here what we do, we use a small dog bone shaped specimen. So, it is a dog bone shaped specimen which we use here, and which is subjected to tension at a constant rate, and this rate is 1 mm per minute, and we apply a load of 500 Newton, and we apply the load until the sample will break. So, you can imagine it to be like this. So, if it is a dog bone shaped specimen, it will be something like this. We are applying a load and we are applying a load till the sample will break from the middle, and we will monitor how much the length is changing before failure. So, we calculate failure strain, which is defined as the change in length to the effective gauge length. Now, what is gauge length or effective gauge length? This is from neck to neck, from here to here, alright. So, this is the effective gauge length L. It has to be again noted that here we are we are trying to see the maximum stress in the material at which we are basically measuring the failure strain. So, this maximum load may not be similar to the actual breaking load. So, the breaking load may be higher than the load at which the stress is maximum, alright. So, these again are few pictures. You can see you have a standard specimen. This specimen is being pulled from both the sides. We are trying to calculate the failure strain, which is change in length to the effective gauge length here, alright, and the stress is P by A, where P is actually the maximum load or the load at which the stress is maximum, not necessarily the breaking load. Okay, so, if we now see the criteria given in the super Pave grading system. So, for low temperature cracking, it is carried out on long term aged specimen, as we discussed. Test temperature is 10 degree Celsius higher than the lowest temperature. We are basically using a BBR and DTT to do the test. In BBR, the criteria is that the creep stiffness should be less than 300 MPa. So, M value should be greater than 0.3, and the minimum strain or the failure strain should be at least 1% in the DTT test, alright. So, these are the criterias which should be satisfied for the selection of the appropriate binder in the super Pave grading system. So, today we will stop here, and in the next presentation we will continue from where we have left, and we will try to see that based on these criterias how a PG grading is actually defined, and again some of the additional important points related to the PG grading system, and also we will discuss about the PG plus specifications, which presently is very popular, especially for polymer modified binders, for which the normal specifications or the normal super pave grade specification fails to meet the desired criteria. Thank you.